of a group. And some of you may know, my original research field is X-ray astronomy and physics of neutron stars. So this is not the main topic of today, but neutron stars are remnant of supernova explosion and the very massive stars, and also the ideal laboratory for the very extreme physics. For example, which sometimes have the very strong magnetic field, 10 to the power of 10 to 11 Tesla, and some of them are called magneta. That is my original expertise in X-ray astronomy. And before coming to RIKEN, I was at the Kyoto University, and before the Kyoto University, I was working at the NASA's Goddard Space Flight Center, close to the Washington, D.C., as a member of the NASA X-ray Observatory. Now it's on board ISS. The NASA represents a neutron star interior composition explorer, which aiming to determine the equation of state inside the neutron stars via the X-ray pulse profile study. So I will have some chance to introduce this very attractive X-ray instrument on ISS. I have been working as the chair of the one of the science groups of the NISA team dedicated for the magneta and some magnetospheric science on NICER. And this is a NICER image, which has 56 modules on a very compact X-ray telescope. But today's topic is for the lightning and thunderstorms. And this is a 3D image of the so-called terrestrial gamma ray flash, or TGF, discovered by the gamma ray satellite, which originally launched to study the cosmological gamma ray burst. So this is related on lightning with the thunderstorms. And you can see this light curve detected by the gamma ray satellite. This is the millisecond gamma ray burst and the spectra up to 20 MeV or something more above the thunderstorm. This is the electron acceleration by the strong electric field at the lightning discharge in the thunderstorm. So this is a quite new discovery in 1990, and nobody knows the lightning can emit the high energy radiations, X-rays or gamma rays. Before that, people believed that the lightning only emit the up to ultraviolet light, or of course radio and optical. So this is quite new field. And after that, some high energy researchers are trying to build a new field, so-called high energy atmospheric physics, related on lightning and thunderstorms. So this is related on electron acceleration. So radiation from electrons are accelerated by the strong electric field can make some Bremsstrahlung emissions in the atmospheres. So this is very important because in some of the high energy astrophysics, astronomers want to know the particle acceleration, which eventually observed as the cosmic rays. And also in atmospheric science, the huge mystery is the origin of the lightning, or the trigger mechanism of the lightning discharge. An interesting possibility of this is the cosmic ray can induce the lightning due to the very high energy electron acceleration. So this is still an open question. And somehow the interdisciplinary field of the high energy astrophysics and atmospheric science. I'm an experimental physicist to love to make some gamma ray monitors or X-ray detectors, and the methodology of the radiation measurement in high energy astronomy is essential to tackle of this field. And from my PhD days, we started to observe the winter thunderstorms along the Sea of Japan, because that is the ideal target to study on this. For example, the gamma rays can only fly a few hundred meters in the atmosphere. So usually we need a satellite or airplane above the thunderstorms to detect the gamma rays from the lightning discharges of thunderstorms. However, only in Japan and also some very limited occasion on the Earth can detect the gamma rays from the ground. And Niigata or Kanazawa are these kind of the ideal locations. And we have been making some observation campaign with our own developed and on-ground detectors. So this is the right figure, right photo is my PhD days. And after moving to Kyoto University, we started to a new project to distribute the small and the compact and portable detectors along the Sea of Japan. So this is one example. And what kind of data we can obtain using these data? This is just one example from our campaign. The left top panel shows the gamma ray enhancement when the thunderstorms passed above our head. And you see that this is the green is a cosmic ray background. And at the center, you see the few minute enhancement of the gamma rays. That is coming from the thunderstorms. And the bottom is a detected spectra of these gamma rays, which extended up to 10 MV or sometimes more. And the mechanism of this gamma ray emission is still open question, but many are expecting something like this. In the thunderstorm, there is an upstream and water particles is hitting with each other, making some charge separation, positive to the top and negative in the bottom. And sometimes this kind of charge separation could be more complicated. And at the very developed thunderstorms, you'd see the three-layer structures. And at the bottom of the thunderstorms, you might see the positive charges at the bottom of the thunderstorms are negative in the top. And there are strong electrical field between these two charge layers. And if the cosmic rays or cosmic ray shower can provide the, some seed electrons, which could be accelerated by this electrical field and suffered from the avalanche multiplications, making many seed electrons on this process. Eventually, they hit the atmospheric nuclei, emitting the gamma ray photons towards the ground. So this is an expected mechanism to detect these gamma rays. And we have been already detected many these kind of events in the city side of Kanazawa area. Some of you might want to know a bit more detailed physics here in the acceleration. In the atmospheres, the high energy electrons have two physical processes. One is the ionization, which loses energies with exciting or ionizing atoms in the matter, and the brainstorming is emitting the gamma rays. Then it hitting the nuclei. So this plot shows the energy loss per unit scale as a function of the kinetic energy of electrons. So these huge mountains in the lower energy side is an ionization, and in the high energy side, that is a brainstorming, you see. And if we have very strong electrical field, all the electrons can be accelerated from the thermal energies in the left-hand side. And in the laboratories, we can make some lightning discharges with this breakdown field. However, interestingly and mysteriously, inside the thunderstorms, we can only measure very low intensities of electrical field. For example, 0.3 megavolt per meter. So the mystery is how the lightning can be happen in the thunderstorm. And you can imagine in the lower energy side, the ionization is very strong. So the electron cannot be accelerated even in the electrical field. However, around the 1 MeV, electrical field exceeds the drag force or the energy loss of the electrons in the atmosphere. Only in this energy range, electrons can be accelerated up to 10 MeV. That could be consistent with the highest energy, which we observe on the ground. So this is one hidden mechanism of the acceleration. So I wrote some introductory review articles in Nihon Butsuri Gakkaishi, so you can see in more detail if you want. And one story on this, we originally started this project from the academic crowdfunding when we failed to get the Kakenhi the research fund from the government. And we try to get a 100万円, $10,000 corresponding money. That is the goal. And for 2 months, we eventually get 160万円 in total from 153 supporters to launch the project. And also one expected discovery is this, a photonuclear reaction triggered by the lightning. So this became a Nature paper in 2017. So I need to skip some detail, but at the lightning, after the lightning, we detected the neutron signal and some enhancement 40 seconds after the lightning. You can see from the left panel. If we extract the gamma ray spectra of this enhancement, we detected the electron-positron annihilation signal clearly at the 0.1511 megaelectron volt. That is a very clear signatures of the existence of the positrons after lightning discharge. The question is what kind of mechanism can generate the positrons at the lightning? This is a mechanism which we are expecting at the lightning. So lightning, like a TGF, terrestrial gamma ray flash, can generate the gamma rays hitting to the nitrogen nuclei in the atmosphere. And this will kick out the first neutrons in the atmospheres, and nitrogen-14 is changed to the radioisotope nitrogen-13. This is a photonuclear reaction seen in a textbook. And this radioactive isotope has a half-life of about 10 minutes and gradually decay to a stable carbon isotope, carbon-13, with emitting a positron. So this is beta plus decay. And the first neutrons is scattering in the atmospheres and again absorbed by the nitrogen-14 in the atmosphere. The most of them go to the carbon isotope, carbon-14. But a few percent of them go to neutron capture with generating the nitrogen isotope, nitrogen-15, at the excited level. So this is promptly making the prompt nuclear gamma rays, which become a neutron signal extending for, say, 200 milliseconds. And positrons quickly annihilate with ambient electrons with emitting the annihilation gamma rays at this energy. So this is a decayed emission with the positron signal. So that is our discovery, and that was somehow featured in the world. And the two important things is methodology of high-energy physics become a key to understand the lightning, and we can use the neutrons positrons for this study. And another implication is the carbon isotope is used for the radioactive dating, where people assume the origin of carbon-14 is a cosmically hitting the atmosphere. However, we show that some evidence that carbon-14 can be also produced from the lightning discharge. The question is how much portion of the carbon-14 comes from the lightning rather than the cosmic ray shower. And we are trying to make some new field, the high-energy atmospheric physics, with some multi-point measurement systems. This is what I want to try. And for this purpose, we are trying to make it a citizen science collaborating with citizen supporters to distribute the small detectors around the Kanazawa urban area. And so far, we have distributed dozens of detectors, and our goal is 50 observation sites within a few years. And the purpose of citizen science. So during this gamma ray emission from the thunderstorm, some group in Armenia detected the optical light. So a mysterious optical light, nobody got the mechanism. And we like to make some alert system. So our detectors automatically record the gamma ray histories to send it to the website, and we can make an automatic alert to citizen supporters to ask them to take an iPhone photo of the thunderstorm. This is one thing what I would like to try at the RIKEN Hakubi team. And for this purpose, we are also promoting some citizen science framework, inviting some citizen supporters from non-academic field. And in the US, there is already some successful citizen science project with some many referred journals. So we started some open science group from the Kyoto University, and I also continue these activities in RIKEN. And probably I almost use my time, so I need to skip this. But our slogan is collective power of science, or in Japanese, Kyosogata science. The purpose is to collaborate not only with researchers, but also some citizen supporters. That is a collective, and also our detector system is not only depending on a single huge accelerator, but also well, not only a huge observatory, but we will distribute many small detectors to collaboratively promote some science. And after, I need to skip this, but when I was working at NASA, I was a little bit shocked this scenery on the SpaceX landing when I was invited to see the SpaceX launch in 2017. And I realized that the future astronomy and space science will be changed using this kind of very reasonable price of rocket science. And we are also trying to make a so-called Cubesat, small observatories in the framework of collective power science. And what we are trying to do is to detect the coherent gravitational wave from fast spinning neutron star. So I need to skip this, but if you want to ask me some question, I can say a bit more detail on this. So we are expecting to observe the very bright fast spinning neutron star, that is a Scorpius X1, with a Cubesat project that is expected to be launched in 2022. And that is a collaboration with the Tamagawa laboratory in RIKEN. So this is a 3D image of the so-called NinjaSat. So NinjaSat is some meaning compared to the huge observatories. And we try to launch the new Cubesat X-ray observatory within a few years. And this is one additional collective power of science, which I'd like to try in RIKEN Hakubi. And this is almost a final slide. And as you can remember, we detect the neutron signal from the lightning discharge. And we are also making some radiation detectors to measure the neutrons. And the neutrons can be used for the lunar exploration to search for water, because the cosmic rays hitting on the lunar surface, and which make fast neutrons. And water, that includes the hydrogen, almost a similar mass of the neutrons, can become some absorbers and also make some scattering of the neutrons. So the fast neutrons and thermal neutrons are good indicators to search for water. So we are trying to make this kind of new neutron detectors to be used for the lunar exploration. That is the final goal, what I want to try eventually from the thunderstorm experiment and the NinjaSat project. So this is the summary. And so our slogan is a collective power of science. And we have been making some so-called thunder cloud project with the high energy physics in the lightning. And we try to expand it to the Cubesat NinjaSat project. And eventually I'd like to try the lunar exploration. So this is our team. And thank you very much for your listening.
Okay, thank you so much for the nice talk. Thank you for covering many things. So if you have any questions, please raise your hand. Hatsuda-san, you can unmute yourself.
Okay, yeah, thank you very much. So just for curiosity, you said that the thunderstorm can produce positron after, the decay of this nucleus. Just for curiosity, can you detect the neutrinos associated with that?
In principle, so neutrons can be generated, and that is transient. So if we have a extremely high sensitive neutron detector, it could be potentially detected. But I have never calculated the sensitivity on this.
Yes. I mean neutrino
yes.
Together with the positron. Yeah.
Yes. If the lightning discharge could happen very close to Kamiokande or the new generation neutral detectors, it could be worth to consider the sensitivity on it.
Okay.
And one postdoc in a group also asked this question, and he's a theoretician, and he's Gabriel Denitz, now working remotely from Brazil due to the limitation to entry to Japan. I'd be happy if some of you could communicate with him for some further discussion on this kind
of. Yeah, great. Thank you.
Okay, any other questions or comments? Chinkai-san, go ahead, please.
So you have some idea to detect the gravitational wave. So I remember the gravitational wave device is very large, but since you use very small device to detect gravitation, so what's the idea for the strategy to detect such small wave?
Yes, we did not write the papers on this project itself because that is a NinjaSat project to be hidden until the launch. But I can say the story. In the left-hand side, you see the binary stars. The central compact object is a neutron star. That is the fast spinning neutron stars. And the mass accretion from the companion star. The mass is accreting onto the neutron star with having the angular momentum towards the neutron stars. And once entering the angular momentum, neutron stars will spin up. And the fast spinning neutron star is expected eventually collapse due to the 遠心力って何でしたっけ英語でcentrifugal force. However, from the X-ray observation, we know that the some of this kind of fast spinning neutron star does not go to the extremely fast spinning frequencies. And there must be some mechanism to pull out the angular momentum from the neutron star. The standard theory is accretion disk. Accretion disk can convey the angular momentum from inward to outward. But on the other hand, another possibility is the coherent gravitational wave. If the neutron star is not the extremely, ideally the spherical, if that has some small mountains on the surface, the gravitational wave could be generated, and that can also convey the angular momentum outwards. And the LIGO team have been also studying this possibility to get the fast spinning, coherent gravitational wave from this kind of neutron star, for example, the SCOEX one. And that team have annually or say the regularly published the upper limit of the potential coherent gravitational wave. The difficulty is nobody knows the spin frequency of this neutron star. And this kind of neutron star does not have a coherent pulsation. However, in the right-hand slide, you see the quasi-periodic oscillation that is called a QPO, and following some theories, the difference between these two QPO peaks corresponding to the rotational spin frequency of neutron stars. The interesting possibility is if we monitor the SCOEX1 in X-rays and to monitor the spin frequency, then the LIGO team or any other kind of the gravitational wave detectors can search for the gravitational wave using the spin frequency determined by the X-ray observation. And basically, in the X-ray observation, we can do that. But the problem is that this kind of X-ray source is extremely bright, and the huge and high sensitivity X-ray observatory cannot observe these due to the pile-up effect. Only the small Cubesat can monitor with a very flexible observation schedule. So that is the main purpose of this. However, we can also use this for some other transient targets as well. So that is our story.
I see. So you use the X-ray to help a gravitational team to detect the gravitational wave.
Yes.
I see.
So we
Thank you.
detect the gravitational wave itself.
Yeah, right.
Okay, any other questions or comments?
Okay, can I ask one comment because I can't raise my hand because I'm one of the first. So
Okay.
okay. Okay, so thank you very much. Very fascinating talks. That's very interesting and fascinating. I'm sure that many of our members. So, so just let me ask one very elementary question. So your work is very interdisciplinary. So sometimes we have some difficulty conveying the message to the different disciplines because of the terminology is different or something like that. So I was just curious about the usage of the gamma ray and the X-ray. You use the interchangeably or you don't really distinct those two?
Okay, there is an interesting example. For example, the bremsstrahlung. In the textbook, the X-rays come from the bremsstrahlung.
Yes.
And in some field, if I say the bremsstrahlung gamma rays, that is very strange to some people. On the other hand, in the astronomical field, nobody knows the emission mechanism of X-rays or gamma rays from the observation at the first glance of the data. And for example, TGF, terrestrial gamma ray flash, comes from the bremsstrahlung, but that is called gamma rays. The reason is that the terminologies of the gamma ray astronomy. So that is one example. And originally we were not so careful about the terminology, but I have several experience that from the other field researchers, that is not the gamma rays, that is X-rays, because that is a bremsstrahlung. So we try to be careful on this point. And if we talk to other fields, not the astrophysicists, I would say the bremsstrahlung radiation or light from the bremsstrahlung, but do not use the bremsstrahlung gamma rays at the same sentence. That is to avoid some miscommunication due to only the terminology. And some fields that bremsstrahlung is very strongly connected to X-ray, but in astronomy, that terminology is only depending on the energy range. Probably the hard X-ray band, 100 kb or something like that could be some boundary between X-ray and gamma. I know this kind of difference of terminology. I try to be very careful about this. That is my experience, not the exact answer.
Right. Yeah, well, thank you very much for clarifying that your position. That well, those differences in the terminology are just historically origin. So somehow it stick to some research field that people distinguish the gamma ray or the X-ray. Actually, those are electromagnetic field, wave of electromagnetic field. So we sometimes associate with those in the origin, that as you said. Okay, thank you very much.
Okay, anyone else? If not, maybe we can thank Enoto-san again. Thank you so much for the nice talk.
Thank you very much.